Good morning, everyone. Welcome to another STEM learning session in mathematics. Today, we will be discussing a very important concept in basic calculus, and that is how to solve optimization problems. It has many applications, real-life applications, and later we will be solving real-life examples of these optimization problems. Ito po ang inyong lingkod ng bayan in service to the Filipino youth, your teacher from El Salvador City Division, Mr. June Marlino. Alright, before we discuss and solve optimization problems, let us have a quick review about a very important concept needed to establish a better understanding on how to solve optimization problems. And it is called extreme value theorem. So let f be a function which is continuous in a closed and bounded interval ab. Then the extreme values of f always exist. When you say extreme values, we're talking about the minimum and the maximum values of the function. And they always exist and occur either at the endpoints a or b, or at the critical point or points, because we can have critical points as many, not just one. So, but take note, this critical point should be part of the closed interval given, in this case closed interval AB. Alright. Now, to test our understanding about extreme value theorem, I actually prepared a very simple activity, and that is to find the extrema of the given functions on the given interval, closed and bounded interval -1 to 1. When you say extrema, we are actually asked to determine the minimum and the maximum values of the function. Are you ready? Well, let's answer this all together. For problem number 1, the given function is f of x equal to 3x squared minus 3x plus 4. That's the given function. All we have to do is to get the first derivative of the given function, and to get the critical point or points, we have to equate the first derivative to 0 and then solve for x. Doing so, we have 6x minus 3 equal to 0, we have 6x equal to 3, and we come up with x equal to 1/2 as our critical number. Take note that our critical number again should be part of the closed interval -1 to 1. Now, is 1/2 part of the closed interval given? Well, obviously it's part. The next thing to do is to check the value functions at either first on the endpoints and on the critical number. So let's start with the lower limit of the given interval. So at x equal to -1, let's find out the value of the function. So we do evaluation of function, we simplify, and we come up with f of -1 equal to 10. So that's the value of the function at the lower limit of the given interval. What about on the upper limit of the given interval? So at x equal to 1, we come up with, of course, we do evaluation of function, we simplify, and we come up with f of 1 equal to 4, meaning the value of the function at 1 is equal to 4. Now we are done with the endpoints. This time, let's solve the value of the function at the critical number or the critical point. At x equal to 1/2, we have this one. We simplify, we use PEMDAS, we find LCD, and we come up with f of 1/2 equal to 3.25. Now, this time, let's find out the minimum and the maximum of these values. Well, of course, this is the maximum and this is now the minimum. So therefore, the function attains its maximum value at 10 whenever x is equal to -1, and in the same way that the function attains its minimum value at 3.25 whenever x equal to 1/2. For number 2, the given function is f of x equal to x cubed minus 9x squared plus 15x minus 20. So the same process, let's write first the given, let's get the first derivative of the given function. Now to get the critical point or points, because again critical point is not unique. Okay, so we equate the first derivative to 0 and then we solve for x. Doing so, we have this one. Actually, we can divide both sides by 3, so we come up with x squared minus 6x plus 5. And this now is factorable, the product of the quantities x minus 5 and x minus 1. Of course, this equation is true whenever x minus 5 is equal to 0 or x minus 1 equal to 0. Let's solve now the roots. So x is equal to 5 or x equal to 1. However, is x equal to 5 part of the given interval? Well, obviously 5 is not part of the given closed interval. Therefore 5 is not a critical number to be considered. What about the other number? What about x is equal to 1? Is it part of the given closed interval? Obviously it's part, and indeed it's actually the upper limit of the given interval. So this time we check the value functions at the endpoints and the critical point. So let's start first with the lower limit of the given interval. At x equal to -1, of course we do evaluation of functions, we solve it, we simplify, and then we come up with f of -1 equal to -45. Meaning to say that the value of the function at -1 is equal to -45. What about on the upper limit of the interval, which actually at the same time is also our critical point at x equal to 1? So we substitute, we simplify, and then we come up with f of 1 equal to -13. So at this time, let's find out which is the maximum and which is the minimum. Of course, -13 is the maximum value and -45 is the minimum value. Meaning to say that the function attains its maximum value at -13 whenever x is equal to 1. And in the same manner that the function attains its minimum value at -45 whenever x is equal to -1. But of course class, let me emphasize that we are only talking with the closed interval -1 to 1 as our reference. I hope it's clear. At this time, our main objective really is to solve optimization problems. What is these optimization problems and how are we going to solve these problems? Now, one of the most important applications of calculus is the solving of optimization problems. This is very important because it tries to solve many real-life problems. So later again, we will be solving real-life problems involving optimization problems. When you speak about optimization problems, we're talking about objective function which we try to maximize or minimize. Clear so far? Right, let's continue. Now, these are the suggested steps in solving optimization problems. So, if possible, draw a diagram to represent the problem. Number 2, assign variables to unknown quantities. So, normally we use x and y if you have two quantities. And then we specify the objective function which must be continuous on the very first place, and then we try to identify if our objective function is said to be maximized or minimized, and after that we determine the domain or constraints of the objective function. In this case, the domain should be closed and bounded interval. And lastly, we use the extreme value theorem to get the minimum and maximum value of the objective function. Are you ready? Alright, let's answer some of the problems. For number 1, find the number in the interval -1 to 3 so that the difference of the number from twice its square is maximize. Take note, there is a word maximize. To answer problem number 1, we follow the steps that we presented a while ago. So let x be the desired number. And of course, the problem talks about maximizing an objective function. And our objective function is f of x, which is actually equal to the mathematical statement or mathematical equation corresponding to this phrase. The difference of the number from twice its square. So basically, that's 2x squared minus x. And of course, based on the problem, that our x, the desired value of x, should be within the interval, closed and bounded interval, -1 to 3. Right, so to get the critical point or points, we actually follow the extreme value theorem. We get the first derivative of the function. Now we equate the first derivative to 0 and solve for x to get actually the critical number. And is x equal to 1/4 part of the given closed and bounded interval? Of course, that's very obvious. Alright, at this time, we will be checking the value functions starting from the endpoints and then the critical point or the critical number. So let's solve first the value function based on the lower limit of the given interval. So at x equal to -1, we substitute the value of x, we simplify, and then we come up with f of -1 equal to 3. What about on the upper limit of the given interval? At x equal to 3, we substitute the value of x, then we solve, we simplify, and then we come up with f of 3 equal to 15. Now we are done with the endpoints. This time, let's evaluate the function or solve the value or determine the value function at x equal to the critical point, which is actually 1/4 based from our computations a while ago. Right, so we substitute the value of x, we simplify, we solve, we follow PEMDAS, and then we come up with f of 1/4 equal to -1/8. But take note, class, our goal is to maximize our objective function. In other words, we will try to determine which of these values is the greatest or the maximum. Now, obviously, the maximum value is 15. So therefore, the objective function attains its maximum value at 15 whenever x equal to 3. Now, another way to solve this problem is through simulation, which I actually presented now. So this is now the graph of the objective function, f of x equal to 2x squared minus x. And notice that the function attains its maximum value at 15 whenever x equal to 3. Now, for number 2, find the dimensions of the rectangle with the largest area that can be inscribed in the right triangle with the sides 6, 8, and 10 centimeters if two sides of the rectangle are on the legs of the triangle and if one vertex is on the hypotenuse. For problem number 2, we do the same process. This time actually come up with an illustration. It's good to present problem with an illustration for us to visualize what the problem is all about. So in this case, the length is 6 centimeters, the width is 8 centimeters, and the hypotenuse is actually 10 centimeters. Right, let x and y be the width and the length of the rectangle respectively, because again we are tasked to determine the dimensions of the inscribed rectangle with the largest or with the maximum area. So maximize our area denoted by f of x equal to the product of x and y, where x should be between 0 to 8. Of course, 8 because that's the maximum width of the of the triangle. Now, in this problem, notice that our objective function is in terms of two variables. Now, we cannot simply apply the extreme value theorem in that case. So what we're going to do is to rewrite the objective function in terms of one variable. So in this case, we want our objective function to be in terms of x only. So we want to express y in terms of x and then substitute it here to come up with an equation of one variable only. So doing so, we can actually use the information in the triangle presented. We can actually come up with similar triangles. Now, if we try to solve tangent of theta, that's actually equal to x over 6 minus y, and of course that is proportionate to 8 over 6, and 8 over 6 is equal to 4/3. And then we solve it, we simplify. Again, our goal is to come up with an expression of y in terms of x. So now we come up with an expression of y in terms of x. So what we're going to do is to substitute the value of y in our objective function. So now our objective function becomes x times the product of the value of y, and if we simplify it further, our objective function is 6x minus 3x squared over 4. So right here we are successful in rewriting our objective function in terms of one variable only. So now we can proceed with the extreme value theorem. We try to get the first derivative. We now equate the first derivative to 0 and solve for x to get the critical point or points, no? Because again, we can have as many critical points depending on the problem, for as long as the critical point or points should be within the given closed and bounded interval. So we have that, and then solve for x, we come up with x equal to 4 as our critical number. Now, is our critical number part of the given closed interval? Of course, that's very obvious. So at this time, we now check the value functions based on the endpoints and the critical number. So based on the lower limit of the closed and bounded interval, the area is 0. And based on the upper limit of the closed interval, x equal to 8, the area is also 0. What about the critical point, x equal to 4? 24 minus 12 is simply 12. And of course, again, since our problem is talking about maximization, so obviously the maximum area is this one. So therefore, the area of the inscribed rectangle is maximized at 12 square centimeters, and with a given dimension of 3 by 4, no? Now, another way to answer problem number 2 is through digital simulation. And again, we are tasked to identify or to solve the correct dimension of the inscribed rectangle with the largest or maximum area. Based from our calculations a while ago, the correct dimension should be 4 by 3, which is actually validated based from our simulations right here. Now for problem number 3, a rectangular box is to be made from a piece of cardboard 20 centimeters long and 32 centimeters wide by cutting out identical squares from 4 corners and turning up the sides. Determine the dimensions of the rectangular box that can be formed with the largest volume. Now for problem number 3, the same procedures are being applied. Here I actually presented an illustration for us to visualize what the problem is all about. So the one on top is actually the cardboard. Now we are asked to cut squares along the four corners of the cardboard, and then after that we torn up the sides to form an open rectangular box, the one below it. So notice that the dimension of the squares to be cut becomes one of the dimensions of the side of the open rectangular box. So the question is, what should be the dimension of the squares to be cut along the four corners such that the open rectangular box to be formed attains its maximum volume? Alright, let's solve it all together. Let x be the length of the side of the squares to be cut, and then our goal is to maximize the volume, length times width times height. So that's equal to v of x equal to x times 20 minus 2x times 32 minus 2x, where x is between 0 to 10, because it's no longer possible to come up with an open rectangular box if our x exceeds 10. Right, if we expand this expression of our volume, we come up with v of x equal to 4x cubed minus 104x squared plus 640x. In this case, the objective function is written in terms of one variable, so we can already solve it using the extreme value theorem. Right, so we get the first derivative, we equate the first derivative to 0 and then solve for x. Actually, we can divide 4 both sides, so we come up with 3x squared minus 52x plus 160, and this is now factorable. The product of the quantities 3x minus 40 and x minus 4. Of course, this equation right here is only true whenever the individual, or whenever 3x minus 40 is equal to 0 or x minus 4 equal to 0. Solving for x, we have 13 and 1/3, but take note, is 13 and 1/3 part of the desired value for our x? Obviously it's not, because it's actually outside the given closed interval. So therefore 13 and 1/3 is not actually a critical point to be considered. What about the other root? Okay, now is x equal to 4 part of the given interval? Obviously 4 is part of the given interval, and so x is equal to 4 should be a critical point to be considered. Now we check the value functions. We do it starting from the endpoints. So at x equal to 0 as the lower limit of the given interval, the volume is actually 0. Actually, it tells us that when x is equal to 0, when you are not going to cut any square at all along the four corners, of course you cannot form an open rectangular box. Now, what about on the upper limit of the given interval? That's 10. We try to solve the volume of the open rectangular box. The volume is also 0, because again it simply tells us that it's not also possible to come up or to form an open rectangular box if you're going to cut 10 if you're going to cut squares with 10 by 10 as its dimension. And of course, I'm going to present it later now in our simulations, and it is indeed true from the simulation. Now what about based from the critical point x equal to 4? What's the value of the function? Of course, the volume attains its value at 1152 cubic centimeters. And obviously, since our goal is to maximize the volume, and these values would simply tells us that the maximum value is simply 1152. So therefore, the volume is maximized when the dimension of the sides of the squares to be cut along the four corners is 4. So basically 4 by 4. Alright, so another way to answer problem number 3, or to at least verify our answer, is through digital simulation. So based on this simulation, again, it's impossible for us to form an open rectangular box if the dimension of the squares to be cut is 0 and 10. And based on this simulation, our calculations are actually proven to be correct, such that the correct dimension of the squares to be cut should be 4 by 4 for the open rectangular box to attain its maximum volume at 1152 cubic centimeters. Alright, as of this time, it's about time to check your understanding about our discussions for today. So I actually prepared an assignments for you to work on. There are 3 problems now. So for problem number 1, determine the dimensions of the right circular cylinder with the largest volume that can be inscribed in a right circular cone of radius 3 centimeters and height of 12 centimeters. I actually presented the digital simulation for assignment number 1 for you to at least verify later on your answers. So, but take note, the presentations are in terms of 2-dimensional axis only, no? But these are actually right circular cone, the one with the blue color, and inscribed it is the right circular cylinder. Now for problem number 2 in your assignment, a wire measuring 12 feet long is cut into 2 pieces. One piece is to be bent into a square and the other into a circle. How should the wire be cut so that the combined area is as small or large as possible? So likewise, I also presented the digital simulation for this problem now. So the line segment with the blue color is to be bent into to form a circle, and the one with the line segment with the green color is to form a circle. And for assignment number 3, I am also interested in gathering your ideas about this, about your feelings. No? So if life is an optimization problem, what is your objective function? And how are you going to maximize or minimize it? So for your answers, kindly send it to the email presented in this slide. So right, thank you so much everyone for listening and watching. Now I hope you learned something from this very simple presentation. Once again, but by the way, if you have questions, if you have clarifications along the way, you can email me through the email that I presented in this slide, or contact me through Facebook. Just search my name for your queries, for your questions. So once again, this is your lingkod ng bayan, in service to the Filipino youth. Your teacher, your humble teacher from El Salvador City Division. I am Mr. Jun Marquinob, saying goodbye. Amping mutanan. God bless everyone.